When evaluating subsets of information inside a linear dataset, you have to read the data sequentially. This class of problems involves operations on a contiguous subarray, or substring, typically with the goal of identifying the longest or shortest valid sequence. The historical, brute force approach to these tasks relies on nested loops. This creates severe n-squared computational waste because the inner loop reevaluates the exact same elements over and over. The sliding window pattern is a heuristic tool engineered specifically to eliminate that redundant evaluation. Identifying these specific constraints allows for the transition from a failing brute force loop to an engineered linear solution. This diagram shows the core architecture of the pattern. It maintains a contiguous subset of elements bounded by two distinct pointers, a left boundary and a right boundary. It operates on dual action logic. The window expands its right edge to explore the dataset, and it shrinks its left edge to satisfy specific constraints. We can apply this architecture to a classic case study, finding the longest substring without repeating characters in this array. To do this, the algorithm requires auxiliary memory. We use a hash set as a secondary tracking tool to monitor exactly which characters currently exist inside the window boundaries, alongside a counter for our longest result. The state management objective is the synchronization of the geometric window, the physical pointers, with the logical memory stored in the hash set. Failing to coordinate these two elements during boundary shifts is the most common point of failure in technical interviews. The complexity of the pattern lies in maintaining absolute state consistency as the window's boundaries change. Here we have a three-part UI establishing our starting conditions. We initialize the left pointer at index 0, an empty set, and the result metric at 0. The evaluation cycle begins with the right pointer at index 0, reading the character A. We execute the inclusion logic. We check the set, confirm it is empty, add A to memory, expand the window, and update the result to 1. We advance the right pointer to index 1. The character B is absent from the set, so we add it, stretch the window, and update the result to 2. Advancing the right pointer to index 2 gives us C. We add it to the set, and the result climbs to 3. During this initial expansion phase, the system operates under ideal conditions. All incoming data conforms to the required constraint. The result variable is passively tracking the maximum size of the window recorded thus far. Expanding the right boundary follows a simple logic. The algorithm must transition to a recovery state only when it encounters invalid data. We advance the right pointer to index 3 and hit our first collision point, the character A. The core constraint of no repeating characters has now been explicitly violated by the current boundaries. A common misconception is to completely reset the window back to index 0. Doing so abandons progress and recreates the n-squared computational failure of a brute force loop. Instead, we introduce the shrink phase. We systematically increment the left pointer to purge state rather than restarting. The precise eviction process dictates that the specific character located at the previous left index, which is A, must be removed from the scene set. By removing the original A, the window state is restored to validity. This permits the new A at right index 3 to safely enter the set, while our result metric safely holds at 3. The left pointer acts as a hunter. It moves forward with the sole purpose of evicting the precise element causing the collision. We'll fast-forward the operational trace to a critical edge case occurring at right index 6. Here is our new target collision. The algorithm evaluates a B, but a B already exists in the current subset. We initiate the shrink response by incrementing the left pointer from index 4 to index 5. We execute the required memory eviction for the character left behind at index 4, removing A from the set. Re-evaluating the constraint reveals a critical failure. The target character B is still present in the set. A single left pointer movement is insufficient. The eviction phase must operate as a continuous while loop until the constraint clears. So we increment the left pointer a second time, pushing it from index 5 to index 6. We evict the character newly left behind at index 5, finally removing the old B from the set. The constraint is satisfied because the specific obstructing character has been successfully purged. We finalize the operation by legally adding the new b at right index 6 into the scene set. Note that the left pointer essentially bulldozed forward. It discarded perfectly valid data, the a at index 4, just to reach and eliminate the one violating element. Dynamic state eviction, executed via a continuous loop, is the precise mechanic that allows the algorithm to heal its constraints without ever restarting the search. Look at this complete historical timeline. It explicitly maps out the path taken by both the left and right pointers across the entire array. Observe the strictly unidirectional movement. Throughout the entire trace, neither pointer ever reversed direction or moved backwards. This physical, forward-only movement translates directly into big O time complexity. Processing an n-element array results in a maximum of 2 n-pointer visits. Because each character in the dataset is visited a maximum of 2 times, once by the right pointer and at most once by the left, the operation mathematically drops to strictly linear O of n time complexity. The rigorous unidirectional pointer movement directly eliminates n-squared computational waste. The sliding window heuristic relies on an inseparable dual-phase architecture. The expand phase constantly pushes the right pointer forward to aggressively explore the dataset and capture new information. The shrink phase pushes the left pointer forward in a targeted loop, stepping in strictly to prune invalid data and restore equilibrium to the system. Mastering the sliding window pattern is about trusting the forward momentum of your pointers, always advancing, adapting to constraints, and never retreating.